podcast is brought to you by LMU Munich.
So let's start by thanking the organizers for putting up this splendid conference in these beautiful surroundings and giving me the opportunity to speak. So I want to speak about a work she has already alluded to, which I've been doing with Rajesh for the last 2 years or so. So I want to briefly review what we've been doing, but basically I want to concentrate on the more recent analysis that we put out 2 months ago that describes on a very quantitative level the agreement between the symmetries of the higher spin theory on the one side and the conformal field theory on the other. So let me just start by way of a motivation that the way I like to think about this whole subject is that these dualities between the Vasiljev higher spin theories and CFTs are some sort of simplified version of a general ADS-CFT correspondence. They correspond to a specific corner in the sort of general ADS-CFT world. And I think it's an interesting corner because it's a corner where you can hope to understand the duality explicitly, maybe prove it, because it's really a duality of the tensionless limit, which you can describe from a weakly coupled point of view in terms of this higher spin symmetry being dual to a weakly coupled gauge theory. So there's some chance to prove it and then maybe to go from there to derive the ADS-CFT correspondence more generally. I think it's also interesting because it may shed light on how one really should think about quantum gravity from the dual field theory point of view, and I shall comment on that later on in my talk. So as she already described, this idea is an old idea, but then there was a concrete proposal in 2002 by Klebanov and Polyakov and Seskin and Sandel that argued that the Vasiljev higher spin theory in ADS4 is dual to the three-dimensional ON vector model in the large N limit. And as he reviewed, there are different versions depending on whether you take bosons or fermions and whether they are interacting or free. And I think this whole subject took a sort of boost through the very impressive work of Gaberdiel and Yin, who managed to compare 3-point functions between the two sides and found a precise agreement. I think this was a very non-trivial quantitative test of this duality, and I think convinced a number of people that there's really something in it. I should also mention that, as he also reviewed, there have been various generalizations more recently proposed between parity-violating versions and so on, and now there's ideas of how to embed this into string theory, but you've just heard all of that. So the version I want to describe here is in 1 dimension lower. It's between 2-dimensional conformal field theory and higher spin theories in 3 dimensions. And from my point of view, part of the motivation is that both sides are sort of better under control, simpler to study. As you will see, higher spin theories in 3 dimensions, or as he also mentioned, are simpler to describe in terms of Chern-Simons theories. And 2-dimensional CFTs are very well understood. We have lots of exact knowledge about all sorts of aspects of 2-dimensional CFTs, and therefore we should be able to understand this duality in a lot of detail. Another motivation, in some sense a posteriori, is this a nice paper of Maldacena. So there's a piece missing here. There should be a reference to Maldacena and Ziboyedov. I'm sorry for that. Somehow my slides don't quite seem to fit. So they pointed out that 3-dimensional conformal field theories with an unbroken higher spin symmetry and a finite number of degrees of freedoms are necessarily free, but this argument doesn't hold in 2 dimensions. In 2 dimensions, there are interacting higher spin theories, and we shall see this explicitly. So 2 dimensions, in some sense, richer, if you wish. So the 2-dimensional proposal that we made takes the form that you should look at ADS3, the higher spin theory in ADS3. There's actually a 1-parameter family of such theories that's labeled by a parameter lambda that you should identify with the 't Hooft parameter of the dual WNK minimal models. So the higher spin theory by itself is purely topological, but you should add to it a complex scalar of a specific mass. The mass is actually fixed by the consistency of the higher spin interactions to be given in terms of this lambda parameter by this formula. So the proposal is that the higher spin theory in ADS3, based on this Lie algebra HS lambda that I shall review shortly, and the complex scalar is dual to the large n limit of the WNK minimal models, where you scale n and k while keeping n over n plus k fixed. And you identify this parameter with the parameter lambda that appears on the ADS3 side. So I should mention that in the original version of the conjecture, as was also alluded to by Xi, we had 2 scalars, but given our more detailed understanding of the symmetries, that is the main topic of my talk, we now think that one of them should be rather thought of as a non-perturbative state, whereas only one should be really thought of as a perturbative scalar in the gravity theory. And as also Xi mentioned, and this is sort of partially the reason for their proposal to look at something somewhat similar, is that this resolves various puzzles regarding the structure of the 1 over n behavior of the structure of the correlation functions. But that will hopefully become clear later on. So in the rest of this talk, what I want to do is I want to explain to you a little bit the duality in a little bit more detail. I want to explain to you how you describe this higher spin theory in 3 dimensions. And then what I want to concentrate on is how you understand that the symmetries on the bulk side, on the higher spin ADS side, are the same as the symmetries of the WNK minimum models. And as we'll argue, that's actually true not just in the 't Hooft limit, but actually at finite n and k. And therefore, that allows you to really understand the higher spin theory at finite central charge, and therefore some sort of quantum version of it. And then I'll comment on the spectrum and the implications of this symmetry match on the spectrum, and then I shall conclude. So, as was, again, I shall say these words many times, as was also reviewed by Xi, he explained that pure gravity in ADS3, at least as regards the classical equations of motion, can be described in terms of a Chern-Simons theory based on SL2, and that's an old work from the early 80s. And now the idea, or one version of describing this higher spin theory in 3 dimensions, and that's part of the reason why it's so much simpler than the 4-dimensional version, is that you can describe the higher spin theory by replacing this SL2 by an infinite dimensional Lie algebra that I call HS lambda, and I'll say a word about HS lambda on the next slide. And what this will do for you is it will give you a higher spin gauge theory that has gauge fields of spin 2, 3, 4, 5, and so on, all the way up to infinity. So this is what you can't read down here. Now the higher spin algebra HS lambda is a conventional Lie algebra. It's infinite dimensional. There is a very simple description of it. You can write it as the universal enveloping algebra of SL2 divided by a quotient. You can write down commutation relations for it explicitly. It's totally concrete and explicit. But the way you should really think about it is that it's the analytic continuation of SLN. So if you've ever asked yourself, what is SLN for non-integer n, then the answer is it's this Lie algebra HS lambda. And the reason for this is that if you choose lambda to be equal to an integer, then this Lie algebra acquires a gigantic ideal, and if you divide out by this ideal, the algebra is isomorphic to SLN. So it's the non-integer generalization of SLN to arbitrary real or complex parameters. And that's the algebra whose Chern-Simons theory describes this higher spin theory in ADS3. So from a modern point of view, how would you think about identifying the dual CFT? What we would do is you would follow the analysis of Brown and Henault and study the asymptotic symmetry algebra of that higher spin gauge theory. So recall, if you do this for pure gravity, what Brown and Henault tell you is that the asymptotic symmetry algebra is the Virasoro algebra. And when you do this for this higher spin algebra based on HS lambda, then what you find is that the symmetry algebra that controls the boundary CFT is the algebra that you call W infinity of lambda. That's an algebra that was first constructed by Figueroa O'Farrell in the early 90s. And it's generated by, unfortunately you can't read this, by one Virasoro primary for each spin, 2, 3, 4, 5, 6, and so on. So this, I should really say that this is where this whole sort of subject started with the work of Henault and Ray and Campoglioni, Fredenhagen, Pfenniger, and Tyson from Potsdam. They studied this algebra for Henault and Ray for lambda equals to a half, and Campoglioni et al. For lambda equal to n. They looked at they recovered the Wn algebra as the asymptotic symmetry algebra, and then together with Tom Hartman, we studied the case of general lambda, and we showed that the asymptotic symmetry algebra is this algebra that was previously described by Figueroa O'Farrell. Now, I should say that just as in the calculation of Brown and Henault, when I write algebra here, what I really mean, it's a Poisson algebra, and it's really given in terms of Poisson brackets, so it's in some sense a classical construction. And part of the game that we'll have to understand is how to quantize this algebra in order to compare it to the honest quantum algebras that appear on the dual two-dimensional CFT. So the usual argument that I've alluded to is that the dual CFT should therefore have this symmetry algebra, and the basic idea that I shall explain to you below is that you should think of this algebra as being the limit of n goes to infinity, or I should rather say of n and k goes to infinity, of the Wn level k minimal models, where you take n and k to infinity while keeping lambda fixed, i.e. you describe it as the 't Hooft limit of the two-dimensional CFTs. Now, I should stress that this is not at all obvious, and this is what I'll spend most of my lecture explaining to you why this is true. And I think we can now effectively prove that it's true. But before I do that, let me just remind you what these Wn minimal models are. These are cosets. They are cosets of the form SUN level k plus SUN level 1 over SUN level k plus 1. And if you are not that familiar with cosets, maybe you are familiar with the Virasoro minimal models. This is the incarnation when you pick n equals to 2. So for example, if you choose n equals to 2 and k equals to 1, that's the Ising model. N equals to 2, k equals to 2 is the tricritical Ising model, and so on. And you should think of this as being sort of higher spin analogues of the Virasoro minimal models that are generated by spin fields of spin 2 up to n. And even if you don't know the details, and I shall not explain them to you today, what you should take away from this is that we know essentially all we want to know about these two-dimensional CFTs. Coset CFTs are very well understood. We know the spectrum of primaries, we know explicit formula for the characters, we know fusion rules, we know whatever you want to know. These are extremely explicitly known two-dimensional conformal field theories. I should also mention that the central charge basically goes like n, because you see n over n plus k and n plus 1 over n plus k plus 1 are basically lambda, so this will go like n into 1 minus lambda squared. So you can think of them as being vector-like theories whose degrees of freedom scales like n rather than like n squared. Now, as I was already saying, on the face of it, these two symmetries are not at all the same. I mean, both of them are W infinity algebras in the sense that they have infinitely many spins, but there are many ways in which you can have infinitely many spins, and therefore you have to think about whether they are actually the same. Now, first of all, they are not the same at all because this is a classical Poisson algebra, so it's a commutative algebra with Poisson brackets, and this is some real Lie algebra or some W algebra. So in order to really compare, you have to understand the quantum version of this asymptotic symmetry algebra. And what I want to explain to you is that you can actually do this explicitly and construct what this quantum version is. So this is what we've done recently in this paper of a little while ago. So there are really two steps to this argument, so let me illustrate them with an example. So the complication arises because this Poisson algebra contains bilinear terms on the right-hand side. The Poisson bracket of W of the spin 3 field with itself, if you convert it into commutators, will give you a term that's non-linear in the L generator, in the stress energy generator. So while you can write down this commutation relations directly taking the Poisson algebra and making it into commutators, if you do it, this algebra will not satisfy the Jacobi identity. And the problem is the nonlinear term. The nonlinear term, you have to pick some normal ordering prescription, but even after you've picked it, they're going to, when you calculate the Jacobi identities, you'll pick up sort of correction terms, and the correction terms will violate the Jacobi identity to order 1 over C. Now, there is a cure to this, and the cure is a very specific cure. What you have to do is you have to replace this by a very specifically normal ordered product. And the remarkable thing is that you have to change this coefficient by C by a finite amount. You have to you shift this 1 over C by 1 over C plus 22 over 5. And when you do that, then it satisfies the Jacobi identity. And as far as I can tell, that's the only way you can make this to satisfy the Jacobi identity. So that's what you have to do for the commutator of W3 with W3, and then you do the same thing for the commutator with W3 with W4, and W4 with W4, and so on and so on and so on. Now, unfortunately, there are infinitely many such terms you have to look at, and we don't have infinite time, so we can't do it for all of them, but we've done it for the first 10 or so commutators, and this story always works like that. There will be a specific normal ordering prescription and a specific, if you wish, one loop shift of the central charge that you have to do in order to satisfy the Jacobi identities to the level that you can calculate. So we are confident that that will continue for all spins, but we haven't checked it. We can't check it. Okay, that's sort of step 1. Now the second step concerns the structure constants that appear. So let me write this commutator in terms of sort of OPEs. So if I write them in terms of OPEs, I would write it as saying that the product of W3 contains the identity, the stress energy tensor, this normal ordered product, and a spin 4 field. Now obviously you can rescale your fields anywhere you like. So let's rescale the spin 3 field so that the coefficient of the identity is C over 3. That's in some sense a canonical normalization. And then let's choose the normalization of the spin 4 field so that the coefficient there is equal to 4, say. That's, for reasons I'm not explaining, also a natural normalization. But then you see you fix the normalization of the spin 3 and the spin 4 field. And if you calculate the OPE of the spin 3 and the spin 4 field, the coefficient with which the spin 3 field appears is a number you can't change by rescaling your generators anymore. So it's a number that will characterize the algebra. Now, if you do the classical analysis that I did with Tom, what you find is this parameter is a certain function of lambda, namely it's 64 over 5 lambda squared minus 9 over lambda squared minus 4. But because you know already that you potentially will have to modify your structure constants by 1 over c corrections, we take the open-minded point of view that there may well be 1 over c corrections to it. Now, how can we determine the precise c and lambda dependence of these coefficients? Well, we can use a little trick. I mean, recall that h's lambda, if you set lambda equal to n, there's an ideal by which you quotient that it becomes SLN. And what this should mean is that W infinity of lambda for lambda equal to n, once you quotient by an ideal, becomes Wn. But Wn is a coset, and we know all the representation theory of Wn level k. On the other hand, we can simply go ahead with these explicit commutation relations that we've written down and calculate the structure of the representation theory of this algebra. And when you do this, what you find is that in order for them to match, that's the correct way. You have to choose the c and lambda dependence of this structure constant C433. And you see this has this form because if c becomes large, then this term drops out relative to this, and this term drops out relative to this, and lambda plus 3 times lambda minus 3 gives you lambda squared minus 9, and so on, and the 64 over 5 work out. So this is the correct c and lambda dependence of this structure constant. Now this is again the structure constant that appears in the first commutator. Now if you look at the higher commutators, well, actually you realize that this problem has been studied before by Blumenhagen et al. And Hornfeck in the early 90s. And what they've done in a somewhat slightly different point of view, but essentially equivalently, they've worked out the c and lambda dependence of the next few structure constants as well. Now this looks, if I may say, a little bit like a mess. I mean, it looks very complicated, but actually this has a very simple structure. You see, what you find is, I mean, what this would suggest is that the algebra is parameterized by c and lambda, because for each value of c and lambda, all of these structure constants are fixed. But you see, what actually happens is that all of these structure constants only depend on lambda via gamma, where gamma is the structure constant, the first structure constants I wrote down. So these complicated relations, you can rewrite them in terms of this parameter, this combination of lambda, that is the whole lambda dependence of these structure constants has this very simple form. It's functions of c times gamma, functions of c times gamma. So what this suggests to you is that actually all of these structure constants are fixed by the Jacobi identities in terms of the lower structure constants and c, because if you were to calculate Jacobi identities, these are precisely the sort of relations you would find. So what we've done together with two of my students, Maximilian Kelm and Karl Vollenweider, as well as a postdoc, Konstantin Kando, we've actually worked out the Jacobi identities for the first 10 commutators, for the first 40 coefficients, and we've checked that all of these coefficients are actually fixed by the Jacobi identity in terms of gamma and c, and we've checked this for another 30 or so structure constants. So the whole algebra is fixed by gamma and c. Now, you may think that I'm belaboring a somewhat technical point, but this is an extraordinarily important point. You see, this algebra depends on the central charge, and it depends on gamma. But it doesn't directly depend on lambda. It depends on lambda only via gamma, because that's the only thing that appears in all the commutation relations of the modes. It's all gammas that control all the structure constants. But you see, if you look at the formula for gamma as a function of lambda, then you see that if you fix gamma and the central charge, this defines for you a cubic equation in lambda given gamma and c. And therefore, what this tells you is that there are 3 values of lambda for which the gamma takes the same value, and therefore the algebra is isomorphic. It's directly isomorphic as a quantum W algebra, because the only structure constants that appear in all the commutators are exactly the same, because the parameter that characterizes all the structure constants, this gamma parameter, is exactly the same. Now, if you apply this to the case at hand, that is, if you pick the parameter lambda equal to n, which corresponds to the minimal models, and you choose the central charge equal to the corresponding central charge for the kth minimal model, then you find that the other 2 values of this parameter are precisely n over n plus k and minus n over n plus k plus 1. This is, I may say, not totally obvious if you stare at this function, but it is true. And what this tells you is therefore that the minimal model at level k is actually the same algebra as the W infinity algebra evaluated at n over n plus k, where you mean by that the correct quantization of this classical asymptotic symmetry algebra. It's in fact the only quantization of this classical asymptotic symmetry algebra. I should mention there's also a third solution. You see, the third solution in the 't Hooft limit is just, this is just minus this, and this just reflects the fact that on a classical level, hs lambda and hs minus lambda are isomorphic Lie algebras. All this construction for hs lambda only depends on lambda squared, and therefore you know a priori you should find two solutions. But the remarkable thing is that you find a third one, and that's the relation that relates it to the Wn minimal models. And the point I want to stress is that it's true at finite n and k. It's not just true in the 't Hooft limit, but it's true at any finite n and k, because we've constructed these algebras at finite central charge, and they only depend on the structure constant, and this is all true at finite n and k. I should also say this generalizes some level rank-like duality of coset models that was previously suggested by these authors, but you have to sort of analytically continue parameters in a somewhat complicated way in order to get there, but this is how we got to believing that something like that could be true, but I think we've now given, in sense, first principles proof that it is true. Now there's a comment I would like to make here, which is that the W infinity algebra is non-linear, and as a consequence it doesn't contain the higher spin algebra hs lambda that appears in the Chern-Simons description as a subalgebra. I mean, you naively think of it as appearing as a subalgebra, but if you actually look at the commutation relations, it will have non-linear correction terms suppressed by 1 over c, and hs lambda was a linear algebra. There were never any non-linear correction terms. So hs lambda is not actually a subalgebra of W infinity of lambda, and I think this is the two-dimensional incarnation of the Maldacena-Gribaujedov argument, that the higher spin symmetry is broken once you go to finite c. This is, as I said, the finite c effect. In c goes to infinity, the nonlinear terms go away, and hs lambda is a proper subalgebra, but at finite c, i.e. finite degrees of freedom, hs lambda is not a proper symmetry of your theory, but only this non-linearly defined W infinity of lambda algebra. And obviously, in the Maldacena-Gribaujedov argument, it works for the free theory and also works here for the free theory. The free theory corresponds to lambda equal to 1, and for lambda equal to 1, you can show that this nonlinear W algebra is in fact, after a suitable field redefinition, linear, and therefore hs lambda is actually a true symmetry even at finite c. So what I've explained to you so far is that you should look at the higher spin theory in ADS3. You can describe it as a Chern-Simons theory based on this hs lambda. You pick lambda to be some rational number, n over n plus k, and then you work at c equal to cnk, and then this is the same symmetry as the Wnk minimal model. So you would expect this higher spin theory to be dual to a two-dimensional CFT with a specific higher spin symmetry, and the semi-classical limit will take, I mean, to make contact with the classical Vasiljev theory, you will have to go to large C. So you will have to take the 't Hooft-like limit, so keeping lambda fixed and taking C large, and then this reduces to what we originally proposed. Okay, so this is, in some sense, explaining to you that the symmetries on both sides agree, but we will obviously want to match the full spectrum of our CFT to all the excitations on the higher spin side. Now, for the Wnk minimum models, we obviously know the full spectrum, so we can ask how well are we doing. Well, first of all, the first thing you observe is that the higher spin massless fields, you can calculate their one-loop partition function on thermal ADS, and for a massless spin S field, you get this formula, and therefore, if you put all the massless spin S fields together, you get this contribution to the partition function from the massless higher spin fields. This is like sort of in the topological setting. And what you see is that this agrees precisely with the 't Hooft limit of the vacuum representation of the Wnk minimum model. If you think a little bit about it, this is precisely the vacuum character mod squared of the Wnk minimum model in the 't Hooft limit. So this is obviously not a consistent CFT by itself, because, well, at infinite n, things are sort of a little bit like as you like, but at finite n and k, you certainly know that this is not a consistent CFT, because at finite n and k, the CFT has also these other representations that are labeled by triplets of representations, as always is the case for a coset theory, and there's a compatibility constraint, so de facto it's only labeled by pairs of representations, a representation of SUN level k, and a representation of SUN level k plus 1. So it's labeled by 2 Young tableaus in the nk large limit. So the most simple-minded representations, and Chi also mentioned these, are those where you pick one of these representations to be the fundamental of SUN and the other one to be the trivial representation. And now, what we originally thought of was just to look at the conformal dimensions in the 't Hooft limit, and there you see that both of them stay finite in the 't Hooft limit. Now, at infinite n, you can do what you like, but if you think about taking this theory at finite n, then you should ask, how do these dimensions behave at finite n when I take C large? And now that we understand this Wn algebra for all values of n and c, we can answer this question, because we can study the representation theory for arbitrary n and c. And what you find is that one of these fields in the semi-classical means large C fixed n behaves like a half into 1 minus n, whereas the other one is proportional to C. Now, there are these annoying minus signs, which also Xi mentioned. This tells you that this limit is non-unitary, but we believe for the purposes of identifying what you should think of as perturbative and non-perturbative, that may not be a problem. So what we take this to mean is that these excitations you should think of as corresponding to classical solutions, like black hole-like solutions of the higher spin theory, whereas these should be perturbative scalars. So what we've proposed is that the contribution of all representations of the form that have a 0 in the second entry is accounted for by adding to the higher spin theory a complex scalar field of this mass. As I mentioned before, the mass is fixed by this lambda parameter given the old analysis of Vasilyev. Now, given a mass, you can calculate a conformal dimension by the usual formula, which in 3 dimensions takes this form. So in particular, one solution is 1 plus lambda. And the main evidence that this captures all the contributions from this class of representations is that you can calculate the one-loop contribution of the massive scalar field in ADS3. It's given by this formula, where H is the conformal dimension of the dual CFT field. And therefore, the total perturbative one-loop partition function of our ADS theory are the massless higher spin fields plus a complex scalar. There are 2 real scalars, so this explains the square. And what we've checked, and this is an analytic argument, is if you expand this out as a power series in Q and Q bar, it matches exactly with the Q and Q bar expansion of the CFT partition function if you only include representations of this type. And this works to arbitrary order in Q and Q bar as you take the nk goes to infinity 't Hooft-like limit. So I think this is a strong consistency check because it shows that the partition function of this P's really match precisely the partition function of this perturbative scalar. Now, the remaining states, we would like to argue, should correspond to classical solutions because their conformal dimension is proportional to C. And there was a paper by Castro, Gopaguma, Goodpearl, and Raymakers where they constructed classical solutions of this higher spin theory for a specific class of them, namely those where the 2 labels are the same. These are the light state Chi was mentioning. And then all the other states we would want to think of as being scalar excitations of these, because if you hit a state of the form nu, u with some scalar perturbations, these are things of the form lambda, 0, you're going to produce everything of the form anything, nu. So we believe that all of these states correspond to conical defect-like or classical solutions, where the rest is just the perturbative spectrum that we've matched exactly on the level of the partition function. Yeah, so my time is up, so let me just very, very briefly say there are various generalizations we've studied. There's a supersymmetric version. You can go from the SU version to the SO version. That's more close in spirit to the original O and vector model-like construction. There is this, the black hole story, which Xi already mentioned. I think there are very interesting lessons to understand how these higher spin theories black holes look like. The Goodpearl, Krauss, Ammon, and Perlmutter have constructed black hole solutions, and their entropy can be matched from the dual CFT calculation, which I did together with Tom Hartmann and Kevang Jin, who is a postdoc at ETH. So let me conclude by saying that I think we've given strong evidence for a duality of this type. The higher spin theory with a complex scalar is dual to the 2D CFT in the 't Hooft limit. I think this is a totally non-supersymmetric, I mean, no SUSY at all, but it works very nicely, I think. There are very detailed precision tests you can do, spectrum, correlation functions. I think it lets you address sort of more conceptual issues of quantum gravity in this very simplified setting. And I think there are a number of main challenges. We would like to prove this duality. I think the main challenge is to understand the scalars from the Chern-Simons point of view. We would like to understand the phase structure of the partition function. In principle, we know it explicitly, but it's quite complicated. Given that we have a very precise understanding of this quantum symmetry, you can make precise predictions for what the C-dependence of various quantities are, like the mass of the scalar. So this should correspond to some sort of quantum corrections on the ADS3 side. And finally, I think we would like to embed this into string theory, very much like these papers of last week and the earlier paper of Guillaume et al. And I think there's a certain chance that this may go, but this would obviously be very interesting in order to really match up with the real ADS-CFT correspondence, of which this is just meant to be a simplified version. So I'll stop here. Thank you very much.
Questions?
Hi. These cosset models have RG flows, which are initiated by one of the, I guess, the non-perturbative scalar?
Well, unfortunately, yes. Yeah.
And it would exchange the
So originally,
scalars in infrared?
Yeah. So you're absolutely right. So the field of the form zero adjoint triggers an RG flow that flows from the kth model to the k minus first model. And once at the end point, the roles of f comma 0 and 0 comma f are interchanged. I'm not quite sure what to make of this now with this sort of new point of view. Yeah, this is a good question, whether there is anything that one can learn from it.
One more quick question.
Thanks. Well, you said that hairspin algebra is not a proper subalgebra of the quantum W algebra that you arrive at. Is it really true that the hairspin algebra does not admit any quantum deformation, maybe nonlinear, that still remains a subalgebra of the deformed W?
I think that's probably true. Yeah, I think that's what, I mean, when people tried to construct W infinity algebras in the early days, that's what they did, and they only found one example, which we would, for modern parlance, call W infinity of 1, because that's, I think, the only sort of extension of it, and everything else will have these nonlinear deformations.